3, 2, 1.
A spacecraft intentionally crashed into an asteroid on September 26th.
Oh, wow.
As part of a roughly $325 million mission.
All right.
The collision is part of NASA's Double Asteroid Redirection Test, also known as DART.
This is a first for humankind.
So why did NASA crash a multi-million-dollar spacecraft into an asteroid? And what will scientists learn from it? There are currently over 1 million known asteroids, according to NASA. They vary in size, shape, and composition, and move in different orbits around the Sun. Some even cross paths with Earth's orbit, but typically don't pose a threat to our planet. But asteroid impacts have occurred throughout Earth's history. Scientists believe an asteroid impact led to the extinction of dinosaurs. In order to test one type of technology that could mitigate a possible future asteroid impact, NASA launched DART.
3, 2, 1. And liftoff of the Falcon 9 and DART.
The DART spacecraft launched into outer space almost 10 months ago. The school bus-sized spacecraft traveled millions of miles through space and eventually collided with an asteroid about the size of the Washington Monument. This is NASA's first ever planetary defense test mission.
Planetary defense in general is aimed at finding out what's out there, figuring out if anything is out there that we need to worry about and when we need to worry about it.
Andy Rivkin, an investigation lead on the DART team, identifies asteroids and develops methods to mitigate the risk they pose to planet Earth. He says this real-world experiment will prepare defense methods against future hazardous asteroids.
It's the first time that we are rearranging a celestial body's orbit.
DART targeted the binary asteroid system Didymos, which is composed of 2 asteroids, Didymos, the larger asteroid, and its smaller moonlet, Dimorphos. This is what scientists call kinetic impactor technology, which involves using spacecraft designed to deflect a near-Earth object to change its orbit so that it misses our planet. According to NASA, DART collided into the asteroid at roughly 14,000 miles per hour, and the impact occurred around 7 million miles away from Earth. But navigating a small spacecraft leaves little room for error.
You can't sit there with a joystick and steer yourself in that fast.
This is why NASA created SmartNav, a new technology system that allows the spacecraft to direct itself entirely on its own, without human intervention. Little was known about the composition of Dimorphos before the collision. Only pixelated telescopic and radar images have provided small clues about its surface. But now, scientists will be able to study images of the crash, which were captured by an Italian CubeSat called LICIACube. The images will help scientists determine what kind of impact DART had on Dimorphos, including a potential crater on the surface of the asteroid. Scientists are also researching how the impact changes the asteroid's orbit. Before impact, it took Dimorphos approximately 11 hours and 54 minutes to orbit Didymos, but that is likely to change now.
We don't know if it'll change it to more like 11 hours and 42 minutes or 11 hours and 46 minutes.
In order to measure a change to the orbit, Rivkin and his team will collect data on the asteroid system's light curves, which are measurements of a celestial body's brightness at certain intervals. Using the light curves, scientists will be able to compare the new orbit to the old orbit, showing how much impact DART made during the collision. In October 2024, the European Space Agency will launch a mission called Hera, which will reach Dimorphos in 2026 to conduct detailed post-impact surveys on the asteroid. Hera will advance scientists' understanding of Dimorphos' internal properties and the outcome of the DART test. Though DART is only a test and Dimorphos isn't a threat to planet Earth, carrying out a real-world test will inform scientists whether this type of planetary defense is a reliable option against future asteroids headed towards Earth.
We don't want to add to people's anxieties. We want to demonstrate that we can handle asteroid deflections.